Let me grab my pencils. Welcome back to yet another Æther physics. It's going to be my ninth Æther physics. Today I want to talk about vortex motions, especially the formulas of motions in vortices. Yeah, let's just start with drawing a basic idea of a vortex. So again, I wanted to continue on the video pressure inside the vortex with the basic idea of the vortex being a vortex tube. You can bend the tube and create a ring, but it's easier to keep a tube for us to understand what actually is happening inside the vortex. I'm going to draw a tube, and it's going to be a big tube, so you can see a big tube. Kind of looks like a tube, right? Why do we pick a tube? We pick the tube because vortex motions, vortex itself means that there is a holonomic presence inside the fluid. And why is it holonomic? Because all the particles that are inside what we call the tube will stay inside the tube. And none of the particles that are inside the tube will escape the tube because of the pressure of the outside of fluid. If, for instance, we have a ring vortex, and a ring vortex is being shot across water, the ring vortex would normally have a trajectory straight forward. If we would put a vortex gun here, and we would shoot a vortex in that direction, it would just go straight forward to the other part of the circle. So if we have the top view of this example, when water is not rotating, we have a circle, which represents the plane, and we have our vortex gun here. So this is our gun. The trajectory would be straight across. Maybe to make it a little bit more understanding, this is the center of the vortex tube, and the vortex gun would just go straight across. What is the formula for a non-rotating fluid? What describes the motions of particles inside the fluid? What are certain parts of this equation? Maybe the most interesting part would be the vector of the accelerations that are within the fluid. We write it down as the differential over the vector divided by the differential over time. And u would be a particle vector for motions. So u would be in 3 dimensions. You can write, we can expand this part. So that will be a funny thing to do, expanding a part of this equation. So what does du dt mean? Grab that over here and write it down. So du divided by dt actually means, it's a little bit bigger, we delta u. So this part of the equation can be, this part represents that part of the equation. We can expand this even further because this is only a summary of the 3 dimension. It says that there is a velocity and that there is a difference over time. We can expand this again, this part of the equation, and say that du dt equals, but it's getting a little bit bigger. So you can see that this small part expands to that, which expands to that, which eventually can expand another time. And I think I made a mistake here, because these aren't supposed to be x's, these should be u's. And as you can see, some parts of these equations get expanded. So this part of the equation represents this one, and that one. And you can see multiplied by the vector u, which are here, here, and here. But we're not yet there, because it does not make sense at the moment. Because what is u? What does u mean? To make this equation about displacements over the x-axis in time, in the xyz coordinates in time, we can replace u again with a small different notation. In this equation, we're thinking about fluid particles and we're moving along with the fluid particles. So it's not about a fixed position, it's about moving along with fluid particles. So it explains the movement of fluid particles in 3 dimensions. It is called the Lagrangian, and it is a time differential of the movement of fluid particles. What would be u? U would be the x dt, if I'm right. Again, we're going to expand this equation. It can be a little bit bigger, and we say the difference of u divided by the differential of time plus, and now we're going to change u in a dx dt equation. U would be dx dt. Nobody told me that I wrote something wrong here, because this is supposed to be z-axis, of course. I think I made a small mistake, because I'm still learning u, v, w, whereas we have this vector u over the u, v, and w for being the x, y, z axis, and so we ended up with this equation. The point I'm trying to make here is that whenever we have an equation that is pretty small and easy, you can expand it to something way bigger. What is this part of the equation? So pressure in 3 dimensions, and it's the density. We can expand this equation the same way as we expanded that equation. So the same thing we did here holds here. So we get a dp dx, dp dy, dp dz over the 3 axes times 1 over the density. So as you can see, this delta function here in this equation actually means 3 dimensions. The same principle holds for the central point of gravitation within the fluid. As you can see, this equation expands to a lot of different meanings. And this is only a non-rotational vortex motion. We do not consider the fluid portion to rotate. An interesting fact about the blue part is that that is the basic of the wave equation. So what it says is this part of the equation tells us that the fluid is waveable. I don't know if that's the word, waveable. It can hold waves in 3 dimensions. Awesome, man, awesome. That's a little bit of the basics of physics of non-rotating fluids. The laws in 3 dimensions. The known laws in 3 dimensions. These laws apply to all sorts of fluids. There might be some exceptions because we do not think of friction or viscous forces within the fluid. We just think of a non-viscous superfluid ether. So thanks a lot for watching. I hope you learned something today, and see you next time.